Hello and welcome back. Today we are tackling a hard Leetcode problem called maximum number of K-divisible components. It sounds a bit technical, but it's basically a puzzle about chopping up a tree into smaller valid pieces. It's a great problem for understanding tree traversals. Let's get into it. Here is the setup. We have a tree, which is just a bunch of nodes connected by edges with no cycles. Every node has a value, and we are also given a special number, which we'll call K. Our goal is to remove some edges, essentially cutting the branches of the tree, to split it into separate components. The catch is that for every single component we create, the sum of all the values inside it must be divisible by K. We want to figure out the maximum number of components we can possibly get. Let's walk through an example to make this concrete. We have 5 nodes here. The connections create a tree structure. We are also given a target divisor K, which is 6. We need to find splits where each piece sums up to a multiple of 6. First, let's look at the whole tree. The total sum of all values is 18. Since 18 is divisible by 6, the whole tree itself is valid as one single component. But can we do better? Can we get more pieces? We could try cutting off node 3. Its value is 4. 4 isn't divisible by 6, so that cut is illegal. Same for node 0 and node 4. Their values are too small. What if we group things differently? If we group node 1 and node 3 together, their sum is 12. 12 is a multiple of 6, so that's a valid component. If we cut that off, the remaining nodes 0, 2 and 4 have a sum of 6. That's also a multiple of 6, so we successfully split the tree into 2 valid components. This turns out to be the maximum number of components we can make. Just a quick heads up, we'll be walking through the solution using Python, but don't worry if that's not your main language. I'll be showing the full code for other popular languages like Java, C++, and JavaScript towards the end of the video. The logic remains exactly the same. The first approach, and honestly the most intuitive one, is using depth-first search. Think about it this way. We start from the bottom of the tree, the leaves, and work our way up. For any subtree, we calculate its sum. If that sum is divisible by K, perfect, we've found a valid component. We count it, and crucially, we don't pass that sum up to the parent anymore, effectively cutting the edge. If it's not divisible by K, we can't cut it, so we must add that remainder to the parent node and keep going up. Okay, we've talked about the big picture and the logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first, and don't worry, after that we'll walk through the most important sections together. Alright, here's the Python code for the first approach. We build our graph and then start a DFS helper function. Don't worry if it looks like a lot, we'll walk through the key parts right now. First things first, we need to represent our tree in a way the computer can traverse. We take the list of edges and turn it into an adjacency list. This just means for every node, we have a list of its neighbors. This lets us easily jump from one node to the next. Inside our recursive function, we loop through all neighbors. Since it's a tree, we make sure not to go back up to the parent. We only want to go down to the children. We call the function recursively to get the sum from each child subtree. This is the heart of the algorithm. We add the current node's value to whatever sums we got from our children. We verify if this total is divisible by K by checking the remainder. If the remainder is 0, we've found a valid component. We increment our count and return 0, effectively cutting the connection to the parent. If it's not 0, we return the remainder so the parent can deal with it. Okay, now for the second method, which uses breadth-first search. Instead of recursion, we can peel the tree like an onion. We start with the leaf nodes because they are simple, they only have one connection. If a leaf is a valid component on its own, great. If not, we merge its value into its parent. Then we remove that leaf. As we remove leaves, their parents might become the new leaves, and we keep repeating this process until the whole tree is handled. And here's the code for that BFS approach. We use a queue to keep track of our leaf nodes. In the loop, we pop a leaf, check divisibility, update the parent's value if needed, and then physically remove the connection. If the parent loses enough connections to become a leaf itself, it gets added to the queue. Building on the BFS idea, we can make it slightly more formal using topological sort. This is often called onion sort for trees. Instead of modifying the graph structure heavily, we just track the degree of each node, which is just the number of connections it has. Leaves have a degree of 1. We process nodes with degree 1, and when we're done with them, we lower the degree of their neighbor. When a neighbor's degree drops to 1, it becomes the next node to process. Here is the topological sort implementation. It's very similar to the BFS one, but notice we maintain an in_degree array. This is often cleaner because we aren't modifying sets or removing items from lists, we're just decrementing numbers. The logic for passing the remainder up to the parent remains exactly the same. So how fast are these solutions? Well, in all three approaches, DFS, BFS, and topological sort, we visit every node and every edge essentially once. This gives us a linear time complexity, or big O of n. As for space, we need to store the adjacency list and the recursion stack or queue, which also scales linearly with the number of nodes. So both time and space are big O of n, which is optimal for this problem. Alright, that covers the main solution approaches in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java using the DFS approach. You can pause the video here to take a closer look at the implementation. Note that we use a long for the sum to prevent overflow. Next up, here is the C++ version of the solution. We pass the component count by reference to update it easily during the recursion. Again, feel free to pause and review the code. And finally, here is the solution in JavaScript. I've used bigint here just to be safe with potentially large sums, as is good practice in these types of problems. Hopefully, seeing it in a few different languages helps solidify the concepts. So let's wrap it up. We looked at 3 ways to solve this. The core takeaway is that tree-splitting problems can often be solved bottom-up. Whether you use recursion with DFS or iteration with BFS and topological sort, the math remains the same. Check if a chunk is divisible, count it, and if not, pass the remainder up. Alright, before we go, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems. So if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding and I'll catch you in the next one.